Welcome everybody to the Johnson Matthey Platinum Group Metals Conference, Critical to the Future of Sustainable Technology. So what is the role of PGMs in the future technologies, or those technologies that are going to allow us to have a beautiful, sustainable and successful future as human beings on our wonderful planet? My name is Dr. Sarah Gordon. Now, before we get started, or basically the bit that you have all been waiting for, because of course this is a conference, and Emma, I'm going to invite you to maybe say some words against this particular slide, because of course this is a Johnson Matthey conference. There is a little bit of a legal disclaimer we need to flash up at the beginning in front of you. We will put this into chat as well if any of you want to read this in detail. So now everyone, we're going to move across to the fabulous Detlef, who is going to start sharing his slides right this second. And Detlef is going to give us his perspective, or a slightly different perspective, shall we say, with regards to the role of PGMs in the energy transition. Now, I know that Detlef has another legal disclaimer to show us. So in the competition of who has the prettiest legal disclaimers, we do expect people to be awarding points, for example, in the chat at the moment. But Detlef, we can't quite see your slides yet. There we go.
Do you see it now?
Yes, excellent, cool. So if you want to just hit that presentation mode, and then I think we will be off and running.
Yeah, sorry.
It's okay, no problem.
I'm struggling a bit. So
that's okay. So if you find your mouse and you go down to that bottom right hand corner,
yeah,
and click on the little
no, my problem is the whole window is gone at the moment.
Okay.
I'm sorry.
What I'm going to do, so everybody have a little conversation amongst yourselves. I'm just going to stop your screen sharing.
Yeah, and I do
now
it
on your
again.
PowerPoint, hit presentation mode. So
yeah, now here.
Mode. Oh, okay, that's fine. And then click on that button. That's it, and it should work. I'm hoping.
So it takes a time. Presentation mode.
Yeah.
Yeah, here we are.
There we go. See,
sorry for the hassle.
That's okay. Everyone, please put your hands together for the fabulous Detlef. Thank you very much.
Yeah. Good morning, ladies and gentlemen. And first of all, I want to thank Sarah, Emma, and Rose for organizing this conference. I think it's running incredibly smooth. Just me was bugging it up now at just the moment, but otherwise it runs extremely smooth. A very well done conference. And of course, I also want to thank JM for having me here, being a guy from one of the other precious metal companies. I think that is exactly the right spirit that we need in this industry. Of course, we are competitors on a certain level, but I think it's also very important that we cooperate to make this whole energy transition work. We cannot fight everyone only for ourselves. We need to put all this together. I want to talk about the role of platinum group metals, a little bit more general in the energy transition. Energy transition has also the name of hydrogen economy, call it whatever you want. I think the topic is about getting rid of CO2, getting rid of burning things to make energy. And Moritz reminded us in his opening note, the planet is reminding us at the moment. Yeah, we are getting some hits on the shoulder. Hey, you cannot continue like this. This planet is getting hotter and hotter by the minute. Okay, now let's come to the less beautiful disclaimer. I think the content is pretty much the same. What I tell you here, I believe is true, but I cannot prove everything. And please do not go out and buy tons of precious metal just because I told you so. The energy transition, yeah. Like I said, what is it all about? And being a chemist, I want to step back for a moment and have a look at hydrogen. Why do we bother with hydrogen? Well, first of all, hydrogen is full of energy. Hydrogen together with oxygen creates one of the hottest flames that we have. It's about 3,000 degrees. And here I have to revert for a moment to my German mother tongue. In German, the oxyhydrogen gas is called Knallgas. And I absolutely love this word because Knall means boom. So literally, hydrogen is the gas that goes with the boom. So it indicates there is quite a lot of energy in this gas. And the second thing is, it's not only creating a lot of energy, the really nice thing is it's creating only water as a waste product. So this is exactly where we want to get. There is no carbon involved, so there is no CO2 generated. And how can we make this reaction useful? Well, we have to separate the reaction which runs in the flame and creates all this heat. We have to separate the different parts of the reaction by a membrane, separating the oxidation and the reduction reaction. And you have seen this setup already in March slides, and she had much nicer graphics than I have. The idea is to have a membrane, to have layers which contain the catalytically active platinum group metals. And then you have also other layers like gas diffusion layers, which direct the gases to the reaction. And you have the so-called bipolar plates, which are for mechanical stability and also for directing the gases. And basically, the setup is the same for an electrolyzer or for a fuel cell. It just depends. In an electrolyzer, you put in electricity and get out hydrogen. And in the fuel cell, you put in hydrogen, and together with the oxygen from the ambient air, you create, again, electricity. And this is the reason why the hydrogen is so important and interesting. It can serve as a kind of storage for all this electrical energy, which we can make now in a green way, but we can do so with wind turbines and solar cells, which do not fit necessarily onto all our cars. Yeah, we need to find a way how to move all this electricity into our mobility applications. Okay, hydrogen is very nice. We have seen this, but unless you are, let's say, a big steelworks sitting directly beside a big electrolyzer plant, you might spend a moment and thinking about how can I store and probably transport hydrogen. Yeah, and this is a comparison with other fuels, which we all know quite well, the diesel and gasoline and so on. And we see hydrogen is playing here in the lower right corner. That means on a mass basis, the energy content of hydrogen is quite nice. It's much higher than the energy content of gasoline. That means kilogram-wise, you might need only something like 5 kg to run a car with a normal range that we are used to of several hundred kilometers. But volume-wise, it looks exactly the other way around. Liquid hydrogen has an energy content of about 4 times less than the gasoline that we know so well. And there's one big problem with the liquefaction of hydrogen. It only works by cooling it to very, very low temperatures, minus 250 degrees. And this already uses up about 30% of the energy contained in the hydrogen in the first place. So probably not the best way to deal with this. So most of the time, the hydrogen for mobility application is stored in a pressurized gas tank at 350 or 700 bar. Now I would like to take you on a journey through the value chain of hydrogen. And I want to show you that the precious metal keep popping up in almost every place. And of course, this is a simplified version. Yeah, there are many byways and other methods to do it, but I want to concentrate here on the core of it. And you can see the hydrogen generation starts with, for instance, with PEM electrolyzers, and of course the iridium is the old bull here. You will need the iridium for making the hydrogen. I will show you in a few slides later that also ruthenium might play a role. And of course, for the other side, for the cathode, you will always need platinum to make it work. I will show a little side use of the precious metals. They are not only needed for their catalytic properties, they are also needed for their corrosion protection, because the bipolar plates, some of them are made from metal. And this is an extremely corrosive environment. An electrolyzer or fuel cell, there's a lot of power, there is heat, there is humidity, so you need to do something to protect your metals. And this could also be done, or is done partially, by precious metals. Then I have shown you already that the hydrogen as such is maybe not the easiest way to store and transport all the energy. So maybe you want to do something with your hydrogen. You might want to purify it first. There you could use platinum and palladium. You might want to transform it into something else. Maybe ammonia would come in handy. You would use ruthenium for this, or you could use the hydrogen for methanation, methanol creation, or liquid organic hydrogen carriers. And there again, you would need the pair of platinum and ruthenium metals. March already spoke about the fuel cell. The fuel cell is dominated by platinum. I want to show you that even a tiny little bit of iridium might help also on the fuel cell side. And again, the side use for protecting the bipolar plates, because also the fuel cell have this same build-up. So let's start with the hydrogen generation. I think we have discussed about this already in other talks, but I want to wrap it up again. I think we all agree that there's a fixed supply of iridium worldwide, and happily our numbers look almost the same. So I feel quite comfortable if two companies come to the same number, then probably they are not totally wrong. So we see a fixed supply between 7 to 9 metric tons per year, fresh iridium coming from the mines. And we believe that around 1.5 metric tons can be freed up for the PEM electrolyzer. That means other uses may be substituted or may see a reduction in iridium uses. But looking at it, if we continue like we do at the moment with the current loadings, there will not be enough iridium. So we need to do something about that. And what we are doing is that we are not using the iridium as such. I will show you this in the coming slides, but we use it as Jenny Watts said it so nicely, we have to use it atom by atom. Yeah, it's not enough that just throwing the iridium powder at the problem. You need to think about how can I use the iridium really in a way where it is best. And when we do this, we get to the next generation of iridium catalysts, which require only 0.1 metric tons per gigawatt. And then we see we are already well within the field which is available, so we can build these 70 gigawatts of power until 2030. And we have another idea coming up from research that we also think about mixed oxides. This is what I already indicated. Maybe the ruthenium can replace some of the iridium in the electrolyzer. This would help again getting the iridium loadings down and helping us to make the PEM electrolyzers able to hyperscale. Hyperscale means growing very quickly, because this is what the lawmakers are proposing here. We have to do this quickly. Yeah? We do not want to take too much time to make this happen. So how do these iridium catalysts look like? You see here on the left-hand side, this is the current existing technology which uses iridium black. Iridium black basically is a very finely divided iridium powder. Then the next generation is using already iridium oxide, so bringing down the loading with iridium. And the third picture that you can see is the iridium oxide on a carrier. And this is exactly the idea, making only the surface covered with iridium so that we use each and every single atom of iridium as it is best possible. Imagine when you have an iridium particle, the atoms of iridium on the inside of the particle, they will never have a chance to react because they are just not sitting at the surface. So this is the basic idea. Spread the iridium as far and as thin out as is possible, so to make all of the iridium really usable for the catalytic reaction. And on the right-hand side, you see the last step in this chain will be to replace some of the iridium with ruthenium, and this is something which we are looking at research together with partners. We are partnering here with Sibanye-Stillwater to make this happen, to put even some ruthenium into the PEM electrolyzer. What is the outcome of this? You can see by reducing, by using a coated catalyst, and this is shown at the bottom of this picture. You have the bulk material on the one hand side. On the other hand side, you have small spheres of, let's say, titanium oxide, which you coat with iridium oxide. You can lower the loading to about 70%. We have calculated here a high case and a low case, but the decrease is approximately the same. Or you can look at it from a different angle. You can say, what is the iridium efficiency? That means how much amperes can I pass through the electrolyzer per gram of iridium? This increases by four times. So you can, by using the iridium in a good way, by thrifting it. I think that's the meaning of thrifting, making very careful use of a scarce material. you can increase the efficiency of the PEM electrolyzer very much. And of course, this will make the PEM electrolyzer more competitive. Yeah, so this is when we need less iridium, then more and more people will turn to this technology. But even the other big technology, let's say the alkaline water electrolysis, we see now some literature that maybe even there might be a use for precious metals, not using the usual nickel electrodes, but using something which is also maybe based on ruthenium oxide and other precious metals. Yeah, and okay, very nice. I can now use less and less iridium, but how is the lifetime of my electrolyzer? It doesn't help if I throw out all the iridium and have a very thin layer, and the very thin layer is used up after a few weeks. But here I can show you that this is not happening. This is the benchmark with 2 grams of iridium based on iridium black, and then the green lines are one of our latest catalysts which contain the iridium oxide. And you can see that after a period of aging at the beginning, it levels out and stays stable and is much better than the current technology. And we have used this to calculate a lifetime, and we believe that this iridium catalyst will run about 40,000 hours. And of course, this can be improved further. And the last bit of making iridium, let's say, fly in this market is of course circularity, and that we have heard this also many times now. It is important that the used pieces, the used membranes which are coated with iridium come back, and we'll talk about this later on a few of the recycling slides. We want to get this material back, we want to reintroduce it, and this will reduce also the carbon footprint of the PEM electrolyzer, and we extend the concept of circularity also to the PFSA ionomers. I think there's a typo here, PFAS ionomers, which we are hearing from Martin in a few minutes quite more about. We think these polymers, they are far too valuable to just burn them. So we want to think about concepts where we can recycle both the precious metal and the ionomeric membranes. Okay, now we have created all this hydrogen very nicely. It sits in our tank. So what do we do with it now? Maybe the first step would be that we want to purify it. Yes, so there is maybe a trace of oxygen still in my hydrogen. And of course, you can use again platinum and palladium catalysts, solid bed catalysts, where you just pass the gases over it, clean them, so get rid of any traces of foreign gases and have a really nice, clean hydrogen, which you can use for your further needs. And what could those needs be? I already talked about shortly. Transport and storage of pure hydrogen is maybe not the easiest one. Yeah, compression and liquefaction, they are possible, but they are very energy intensive and expensive. So maybe not the most attractive way to make use of this hydrogen. There are other ideas. There is the solid storage idea. That means you put the hydrogen into a solid hydride, a special chemical compound. This doesn't make any use of precious metals, so I will skip it here. Then the next idea is to use liquid storage. The liquid storage is also called LOHC, liquid organic hydrogen carrier. This is a liquid organic molecule which you can basically load and reload and deload with hydrogen. You can hydrogenate it and you can dehydrogenate it. You can use the molecule as a carrier for hydrogen. The fifth possibility is to make together with CO2, which sounds and looks very attractive at the first look, because we want to get rid of the CO2, you can use the CO2 and the hydrogen to make methanol, methane, or similar compounds. But we have to be honest, the CO2 does not vanish in this application. Once you re-extract the hydrogen from the methanol or the methane, the CO2 will be back. But at least this would open up, let's say, a net zero way of using CO2 to make hydrogen more transportable. And then the last possibility, and we think at the moment probably the most attractive one is not to use any carbon-based chemistry, but use nitrogen. Nitrogen is abundant in air, and you can use the nitrogen and the hydrogen to make ammonia. This has been done for a very long time. You can transform the hydrogen to a gas which is now much more easily handled, because liquefaction of ammonia occurs at -33 degrees without applying any pressure. So this would be very nice. You just cool it a little bit, and then you have a liquid which is easily transportable. So let's have a quick look at the LOHC first. Like I said, it's an organic molecule. You would use a ruthenium catalyst to load it with hydrogen at the point where you make the hydrogen. Then you can put it into a truck, bring it to the place where you want to use the hydrogen. There you would need a platinum catalyst to set free the hydrogen again, and then you can use the hydrogen for your fuel cell or whatever you want to use it for. And then you bring the, so to speak, empty molecule back to the station where you make the hydrogen, and you load it again. A nice circular process. Of course, this is not working fully without any losses, but in principle, you can carry the organic molecule in a circle and use it for transporting the hydrogen. And we use platinum and ruthenium catalysts for this. The next one would be the methanation, which I mentioned. You would need a CO2 source. I think this would probably not work with atmospheric CO2. It would be easier to sit close to a plant which generates CO2 anyway. Take this CO2 from an industrial process, combine it with the green hydrogen that you have made by electrolysis, and then you can generate methane gas, which has the nice opportunity you can feed it into the existing grid. Yeah, so it's compatible with the gas that is already in there. And I already said, this is at least a way of making a net zero energy transport. You need a ruthenium catalyst to make the methane in a nice selectivity, and to use it as a substitute or as an additive for the natural gas. And this works much better with ruthenium than with the conventional nickel-based methanation catalyst. So there are just some chemical advantages when you use ruthenium. Okay, now let's come to the topic of ammonia. Ammonia generation has been there, I think, for almost 100 years now. But I must admit, it's chemistry done the German way. It's chemistry with fire and salt. Yeah, it's 300 bars, 450 degrees temperature, using an iron catalyst. So this is nothing that you can build in a centralized version. Yeah, there is no small plant making ammonia. By the way, the name of this process is Haber-Bosch. So two German guys who invented this. The Haber-Bosch process is one of the classical big processes which work best when you make them as big as you can. But fortunately, there are alternatives. If you use ruthenium again instead of iron, you can think about using much less pressure, something like 90 degrees or 90 bars, sorry, already much more manageable. And then you can think about building smaller units and enabling a kind of decentralized generator for ammonia, which you can use for energy transportation. So once you have made the ammonia, what can you do with it? And I just want to mention this here shortly. It does not belong to this energy mobility topic, but of course, one of the very big uses of ammonia is to use a platinum gauze and make nitrites from it. And this feeds millions and billions of people. It is an old technology. It is not very sexy, but it keeps us alive. We must be very clear on this. Yeah, burning ammonia to nitrate keeps us alive because it enables the fertilizer that keep us feeding all the ever-growing population of this planet. But coming back to the energy topic, in this case, we would probably not oxidize the ammonia, but we would rather crack it. That means we would be using, again, a ruthenium catalyst. This is pretty much dominated by ruthenium, this topic, to set free the hydrogen from the ammonia. This can be done by a relatively simple solid bed reactor. You just pass the ammonia through and you get out the hydrogen again. And of course, these processes, they do not work perfectly. So maybe you have overdone it a little bit and you have also combusted some of your ammonia. That means you have made nitric oxides. And you know, nitric oxides are really harmful. You do not want to have those. So you can always use palladium again to treat your exhaust, to clean your gas, to get rid of the nitric oxides, which is exactly the same thing which happens already in the car catalyst that we are using every day. Okay, so now we have made the hydrogen, we have transported it, maybe we have changed it to ammonia, but now we are at the point of use, and we want to use this hydrogen again. And like Marge already explained, this is of course the theater for platinum. Platinum is used in the fuel cell to remake the electrical energy from the hydrogen. And there's a vast variety of platinum on carbon catalysts. And of course, the topic here is always the same. We want to use as less platinum as possible, but there's quite some variations. Yeah, you can try to, of course, you can optimize your platinum distribution. You may want to optimize also your carrier, because there quite a lot of the activity depends also on the carbon carrier. So it does matter which kind of active charcoal I am using actually. And you can use also platinum alloys, which then contain already a little bit less of platinum. And you can also tailor-made your carbon carriers so that they are really corrosion resistant. By corrosion, I mean, again, please keep in mind, an electrolyzer cell and a fuel cell is a harsh environment. Yeah, you have oxygen, you have hydrogen, you have temperature, you have humidity. So if there is not enough hydrogen, then all these catalysts, they will starting attack the carbon carrier. And this is where now the iridium sneaks in again through the back door. When you use iridium on the oxygen evolution reaction side, it has been shown that it is a very good additive for coping with so-called hydrogen starvation, especially when you are running a fuel cell car. There might always be states where the motor is not running at its best. Yeah, so you have a cold start in the morning, or you are idling at a red traffic light. So there might not be enough hydrogen in your fuel cell, and then you need, for these states, you need something which keeps your system from eating up itself. Okay, so this was the journey along the hydrogen value chain, and now I want to briefly talk about the recycling, because I think this is the last piece of puzzle which fits in here. And of course, I do not have to explain too much about recycling. We all do this for many years. What we do every day is, of course, we take back precious metal containing wastes. We incinerate them. Basically, we get it to a precious metal rich ash, and from this ash we run a wet chemical process, and we can extract and separate and purify all 8 precious platinum group metals again, and give them back to the market, make them useful again. What is today already very well established is, of course, the recycling of catalytic converters, because they are the biggest users of precious metals, and there's a very well established value chain of different companies working together. There's one company scrapping the car. The next one is dismantling and decanning the ceramic body which contains the precious metal from the car catalyst. And somebody is grinding up this ceramic. Ceramic is molten in an electric arc furnace, separated into a slag phase and a metal phase, and from the metal phase you can, which is concentrated in a converter, you can extract from the metal phase again the precious metal by wet chemistry. This is well established for the car catalyst, and I think for the future we need exactly the same for all these catalyst coated membranes, be they from a PEM electrolyzer or from a fuel cell. It doesn't matter. What this looks like is a stack like this. A stack can contain maybe 150 coated membranes, and this is quite a considerable problem. Somebody has to take apart this stacks mechanically, has to separate and take out the coated membranes, and only then we can start to think about the recycling of the precious metal which is in there. And like I already indicated, maybe total incineration is not the best method here. Yeah, we have these very valuable ionomeric membranes which contain a lot of fluorine. if you just incinerate this stuff, you will create a lot of hydrogen fluoride, which will be probably eating up your oven quite quickly and create some problems there. So it is much more intelligent to think about a concept where you take out the coated membrane and then you remove the catalyst coating from the membrane. This could be done mechanically or chemically, and ideally you get a rather clean membrane and you get a rather clean catalyst layer, and then you can recycle both of them in separate ways and make use of the valuable chemicals which are in there. And we are part of some external projects because we do not have all the know-how in-house. Yeah, we are not a maker of perfluorinated polymers, but there are companies out there. And this is what I said at the beginning. We need some kind of team spirit here. Yeah, we need to group up. We joined some European project where we are looking exactly at this. How can we make this happen? I think I do not have to explain why recycled precious metals are so nice. They have a much better carbon footprint. I think this has been mentioned already quite a few times. Even though we incinerate the waste and we create, of course, some CO2 again, it is much less than what is needed or what is created by mining the ores in the first place, because the mining process just needs a lot of energy, and we have learned already about the, let's say, the not so fortunate energy mix in South Africa, which is one of the most important mining countries. So there is the CO2 is created there, and of course it is good to use the recycled metals also to bring down the carbon footprint of any precious metal containing products. And this goes very well together with our own decarbonization roadmap. We as a company, we also want to be carbon neutral. We have set ourselves quite some ambitious goals. We want to be carbon neutral in 2025, use only green electricity. And we want to turn away from fossil fuels by 2033 and run a net zero company where we really do not generate any extra CO2 equivalents. And with this, I want to thank you very much for your attention, and I'm waiting for your questions. Thank you.
Detlef, thank you so much for that. Absolutely phenomenal. Round of applause from all of us here. That was brilliant.